Well, I think my assignment for today is to introduce the topic of the morning, and that is how do we understand the system and how much do we have to understand the system to do effective management of a marine area. And I have just a couple of very general comments that I'm going to make just to hopefully get the discussion moving ahead. But I have a couple of quotes that I'd like to begin with that I think sort of capture the idea that at least I'm trying to convey. And one is from Immanuel Kant. I think you know who Kant is, the German philosopher. He said, "The necessity to decide is larger than the possibility to understand." And I think that's where we are as planners. I mean, we're paid as planning professionals to put together information, to synthesize things, to come up with management plans that have some action implied in them. And we usually have a deadline. We have to make a plan in 2 years or 5 years or something, but there's a deadline. And I think it's important to understand the differences between scientists or researchers and planners, because we're two very different cultures. And usually that's the problem that always happens when we have difficulties in terms of communicating, because we think about problems in very different ways. I mean, a scientist usually starts with some kind of a hypothesis that he's trying to prove, and takes a problem, an interesting problem, to him or her, and tries to break down that problem to a manageable, tractable kind of analytical process. So scientists usually are people who take things apart and study pieces. And it's completely the opposite of what planning is all about, because planners have to put together information, and they're trying to synthesize information into a plan, and then a plan that obviously takes some kind of action. Scientists rarely have deadlines. I mean, some scientists work on the same problem for their entire career, and they know more than anyone else in the world about some little tiny piece of the problem. And that's good. That's what science is about. But planners, again, have an entirely different challenge ahead of them. So there's a very difficult time in terms of trying to figure out how these two different cultures, how these two different groups of humans interact and communicate with each other. So how do we make this better as planners? And I'm sure some of you might be scientists. How do scientists contribute more to the process? It's difficult. That's all I can say is it's hard. It takes a lot of practice, it takes a lot of experiments, and it takes a lot of mistakes, and hopefully we can learn from some of these. Scientists like to work things out, accuracy and precision and things that science is concerned about is a very important value. Planners usually don't care about knowing about a small part of the problem in great detail. Planning is more about direction. It would be good if we had management plans that, when implemented, could move us in the right direction and not necessarily reduce the certainty of decisions by a great deal. We're never going to get it right the first time we make a plan. So we don't want to be paralyzed in terms of action by lack of certainty in information. If we say we're going to get it 75% right the first time through, and we have a system that is really adaptive, and we have monitoring and evaluation that we can learn from, 75% is pretty good the first time. Then the next time we make a plan, after another 3 years, and we learn a little bit more about what works and what doesn't work, and we can get it up to 90%, that's good as well. We're never going to have a perfect plan. There's no such thing as a perfect plan. And planning has tended to try to pretend that the plans are perfect. We used to call these things master plans. Nobody calls them, the planning profession does not use the term master planning today. It might in a few countries, but certainly the mainstream of planning doesn't do master planning. We don't use the word blueprint, although that's very attractive, particularly when you're talking about the sea, to have a blueprint of an area. These plans are going to change. Tisha said yesterday that the Netherlands doesn't even pretend to have a document that's called the a management plan. I'm not quite sure how that works, but I like to have management plans, but you have to recognize that they're not going to be the direction that we're going to take for the next 20 years, because there's social change, technology changes, economic changes, changes in knowledge about systems. We're always dealing with in a changing environment, and planning has to be able to adapt to that kind of environment. Collecting information has always been a problem with planning. We tend to collect too much information. Often we work without a work plan that has allocated very scarce resources to particular parts of the process. So what has traditionally been done in land planning, terrestrial planning, is that we start out by saying we need to know everything. We're going to collect everything we can possibly collect in terms of data and information about a particular place. And somehow answers and strategies and actions are going to emerge from this big pile of data without much analysis. It never works. We have wasted, or we will waste, and we have wasted, half of the resources that we have in collecting data that never is used. So it's critical that we talk to not only stakeholders, scientists may be stakeholders as well, but it's important that we talk to people who know in an objective way what the problems are that we're trying to resolve in a particular place before we start. So we want to have a short list of things that we know are conflicts or that are issues or there are problems that exist that people can relate to, that stakeholders say, yes, I think that's a real problem here, or that politicians can say, I want to be able to resolve this for my constituents so that I can claim that I did something while I was in office. And we need to know what the problems are before we start collecting data. We don't want to just say we need everything, because we don't, and we won't use it. So there is a real requirement to have this kind of communication with knowledgeable people, and again, I certainly would include scientists in that, but we don't want to just go off and start collecting data and information. It would be good if we had perfect information, for example, on the value of ecosystem services, about the value of habitats, the value of different things that nature provides to us, because then we could sort of balance some of the values that nature provides with things like the value of oil and gas development or the value of increased port development. We don't have that information today. We can't sit around and say we want to have a group of social scientists and natural scientists working together to give us that value of ecosystem services before we can say anything about getting started. It's not going to happen. It would be good if we had better information and better techniques to measure the cumulative effects of human activities in a particular region. But we don't. We can do a little bit of that. We can certainly look at individual activities and say, well, the effects of this on the marine environment or so and so. It's not that difficult, and it's not that different from looking at air quality management or water quality management. Those are both fluid environments as well. Things are moving around in the air. Things are moving around in rivers and lakes. So the marine environment is not that different when you really think about it, and we do know how to do effects assessment of particular things. But in terms of the cumulative effects of what happens when you have oil and gas development and port development and sand and gravel extraction and fishing extraction, how does that affect the whole, how do all of those things affect the environment? That's a difficult question to answer, and we are still working on trying to develop better methods for analyzing cumulative effects. In the case of Massachusetts that I mentioned yesterday, they had a year and a half to develop the plan. They had a lot of information available when they began the planning process, but one of the projects that they also wanted to start at the beginning of that planning process was a better attempt to look at the cumulative effects. And they allocated resources to a university to provide those kinds of methods. And as the year and a half deadline approached, they realized that the results from that study were not going to be available before they had to submit the plan. So they said, okay, you folks just keep working on that cumulative effects thing. We'll get you the next time around in the planning process. But there's no discussion of cumulative effects in the Massachusetts Ocean Management Plan. because it just wasn't produced in time. That kind of work does take a long time, and planners have to move on. So I think the idea of perfect matches between the timing and the thinking that goes between planning and science, or research is probably a better word rather than science. That research is simply not going to be available and in the appropriate form to put it into a planning process in a timely way very often. Hang on one second, I had a couple of other thoughts. So I think it's important again to think about what you need of research before the planning process begins. It's important to have a plan, a research plan that is a part of an overall work plan that says we have X amount of dollars, we have X amount of time available in terms of staff, we have a time constraint in terms of getting finished, and we're going to allocate some percent of X to research, applied research, things that we know we need that we don't have, that we can advance our own interests in terms of producing a plan, a good plan, with a little bit of applied research. And we will know better after the first round of planning what we don't know. So you should be able to be smarter as you go through a planning process, and particularly once you start going through a monitoring and evaluation of the performance of that plan, you'll know better the next time around what you really need from the research and science community. Again, I think it's important to use the premise that you're only going to collect what you need. You're not going to try and collect everything, and what you need should be related back to problems that are identified at the beginning of the process. Again, the whole idea is that you're not going to know all the problems. You're going to discover problems as you go through the planning process, but that is just a fact of life that you deal with as planners. You don't want to, again, get caught up with the idea that you need a perfect plan. The perfect is the enemy of the good. Can't remember who said that, but Voltaire, I think. But whoever said that is right. I mean, you're never going to have everything that you need before you begin a planning process. So I think that I'll end up with one more quote from a military person, and that is, a good plan today is worth more than a perfect plan tomorrow, right? If you need it today, you want to have it today. You don't need it perfect sometime in the future. So when we think about communicating with scientists, I think we want to try and keep them focused on what we need, not what they know and what they would promote as something that you really need to do planning. You need to have enough thought from a system standpoint to know how this piece fits with that piece, and that only comes from good planning, not necessarily from good science. That's all I have to say, Andrew. You're back.
Thank you very much.
Okay.
Yes, now the mic is working. No, actually I would like to turn over the mic to Hans. Thank you very much for your reflections, and we will of course come back to them later on. Satte den på mute. So, let's see, that's strange.
Och det är på. Ja.
Now.
Thank you. Yeah. I can only support what we have heard just from Charles about the use of information and data in the planning circle, and from my experience of many years of providing information and data for planning purposes. So, but now I will try to give a very quick overview of what kind of information we have in the Baltic area, and what kind of geophysical properties which could be of value for which are of value for the planning. And this builds on my personal experience. It's not finished. You can continue to work on it. But we discussed yesterday a lot of the different kinds of uses of the ocean and on the sea, and there are a lot of different ways to use the ocean, and there are a lot of stakeholders, as we said yesterday. But when we try to support the planning for these different kinds of activities, of course we need variables which are describing the important properties for the planning purposes or for the use of the sea. And I have tried to list some of them, mainly the geophysical ones, on the top of this diagram, and put across where there is a connection between the use of the sea and a certain variable which we need to estimate or observe. And then I will turn from this to speak about these variables in the Baltic area and how the Baltic in principle works, and what we have to take into account when we are planning. And the most basic thing is of course the topography, and what I'm showing here is only 1 week old. This Baltic bathymetry database was released about a week ago, and it's only a resolution of 500 meters, but it's still a revolution, because this information has been rather secret in many parts of the Baltic for several decades, and now at least we have this 500-meter resolution, and we know that behind that there are even more data. But then you have to approach the hydrographic agencies to get more details. But this is for, let's say, the more general planning purposes. What's typical for the Baltic bathymetry is that we have an entrance which is very shallow, and did you change and then the average depth is 60 meters, so it's not very impressive if we compare with the Atlantic or the coastlines of United States, for instance. We have we have a few deep holes. One east here on Gotland is down to 240 meters around, and we have another even deeper here on the Swedish side, which is about 440 meters. The rest is rather shallow. So it's not a very dramatic topography. The data exists. What's maybe more dramatic for the Baltic is sea level, and sea level is at the moment maybe the most popular planning variable you can find, and we get a lot of questions about sea level, not of this kind at the millennium scale. 18,000 years ago, the Baltic was covered by a big glacier. It was during the Ice Age, and it melted away slowly. And then, about 10,000 years ago, it looked like that. The ice was still there. It was a big freshwater lake which had been built in the basin, and we can understand that we are talking about rather short time scales for an ocean area. So the Baltic is a very young sea, which is still developing. So we shall not be too surprised if we see trends in the Baltic, and we shall not be too scared, because it's still developing to a more maybe final stage. There was one period when we had very high salinities in the Baltic, because across Sweden there were a connection to the world ocean, but that was closed when the land was coming up, because when the ice disappeared, the land were moving upwards. It had been pressed down by the big ice sheet, and then it was closed, and we had a freshwater lake, and then a few thousand years later, it opened up to the North Sea, and we got saline water into the Baltic again, and it's more similar to the situation we have today. But if you can see the details here, the Baltic Sea was much larger. There were a lot of areas covered by the sea in all our countries. What's rather interesting in some of the early pictures is that the North Sea is not existing at all. There lived a lot of people on the North Sea, and this is now a planning item because they want to protect all the remainings from fishery, which you can find on the bottom, because when they are trawling, they are a lot of interesting biological material is coming up, which they are selling instead of collecting for science. So the Baltic sea level has changed a lot through the years, and also in shorter time scales we have a change. We are rather fortunate. We have the longest continued time series in the world on sea level. It's the Stockholm station, which is still running, but with less value today because it's in the middle of the town. But you can see that it's variable between the years. It's annual means. You can see the blue dots, but during about 250 years, the land at Stockholm has come up at least more than 1 meter from its original position, and it's even faster land uplift if we go further north in the Baltic Sea. So in the Gulf of Bothnia, there are places where even during a lifetime you can see new islands coming up. And the towns in the northern Gulf of Bothnia has moved their harbors several times further out into the sea because the land is coming up and moving the harbor from the sea. So this is a reality, and it's observed. It has to be taken into account. But this is in the northern part. If you go to the southern part, I think maybe it's your picture. I found it in one publication. This one, it's Gdańsk, where you have observations, and here you can see that the sea level is going in the other direction. It means that land is sinking here, and of course causing quite different problems. In particular, now when we know that there are expected big changes in the ocean, global ocean sea level. These expected changes, they are discussing it in Stockholm at the moment. There is a UN climate conference, but I haven't got access to the estimates during that. But you can see that there are a list of different estimates. But what we can conclude from this is that it's expected that the world ocean will come up about 1 meter during the next 90 years. It's an estimation for year 2100. This climate change, which we now more or less believe in and have a lot of records showing, it has changed a lot of the planning, at least at municipality level. Instead of just using statistics and maximum minimum value from the statistics, now they have started to use model forecasts to get the right values for their planning. And in particular, if you the towns or harbors in the southern part of the Baltic, both on the Swedish side and on this side of the Baltic, they are more and more concerned in their municipality planning about the changing sea level due to climate, and also the changing amount of water in our rivers, because it's expected we are expected to get much more rain in the future, and the rivers, when they interact with the ocean, then they cause flooding in the harbors and in the coastal towns. We have recent examples from Gothenburg in Sweden where there have been severe flooding some years ago, which haven't happened historically, but it is because of the increasing sea level and the increasing water and flood in the rivers. Then we have short-term changes, and when I did this, I think it was last Sunday or Saturday, this is a week. We are here now in the diagram, and so the blue is the forecast, and the red is the continued validation of the forecast, the station in Gdańsk, which has been used, and you can see that it's about half a meter during 1 week. It can change. This has to be added to all the other variabilities or the changes in sea level, so we do not flood our areas to unnecessary in the future. It's rather high variability, and here I have listed the maximum sea levels in the different parts of the maximum observed sea levels in different parts of the Baltic system. We do not have any tide, so this is depending on weather and wind, and the minimum levels. And if you look at minimum, maximum, it's almost a difference of 3 meters. So in addition to all the other things, you have this variability, and I think in Gdańsk this can cause a lot of problems in the future, that the sea level is rising and it's variable, and it's expected to be more variable with a kind of weather we will have later in this changing climate. And it has to be taken into account in the planning, and it is in many places today, but not always, because if you look at consultants, they still use old statistics and 100-year values for their planning, while it's much more dynamic nowadays, and we need to get much more exact values for our planning. What about the forecast? I checked it yesterday afternoon, and the sea level change was even a little higher than the forecast, which is the blue line. So this 1.5 meter change during just a few days is not fantasy. Very often we get questions about currents. Strong currents is difficult if you have a construction at sea, also for navigation and several things in the ocean. In many places in the world, you do not have to calculate too much to get the currents, because they are rather stable currents. They are well known, but here I have used 2 forecasts: the night which has passed and at midnight tonight. And if you can see the arrows, you can see that the currents are changing very much during less than a day. So when anybody asks, what about the currents in the Baltic? We can say they are very variable. But if we use all our forecasts and make some kinds of statistics, we will find what we call the residual current. And it's very small. Maybe you will talk about now. It's very small compared to the real currents, but in the long run, it creates things as the different spits here down in the Baltic by moving sand in a certain direction. So there is a long-term effect of this small residual current, but you can't measure that, you can't see it. It's just the difference between all the different currents, daily or hourly currents. If we go a little below the bottom, we have 2 typical kinds of bedrock in the Baltic area. Scandinavia and Finland is built on very, very old bedrock, crystalline rocks, stable for constructions, and also old, not it's moving up still, but it's good for constructions, for instance. If we look at the southern or southeastern part of the Baltic, it's a sedimentary rock, bedrock, and with a lot of limestone and sand. If we look at the top of the sediment, and this map is much better when you look at the directly in the computer, but what we can see generally is that it's really created to a large extent by the ice age and the glaciers through the years. And if we look, for instance, at the orange parts, it's sand, and we can be very happy about that along the beaches, in particular in the southern Baltic. It's nice sand beaches. If we move over to the Swedish side or Finnish Swedish side, you can see these red dots. It's a crystalline. Oh, sorry. Ska använda rätt knapp. The red one. I didn't dare to press the red one first. Yeah. You can see the red spots here. It's rock, solid rock coming up. It's a very nice archipelago. It's not very nice for shipping because there's several of these you can't see. While it's much softer bottom here, causing movements of sand and also movements. If you put equipment there, it's very difficult to have it stable. But this is a general picture, and if you want to look further in it, it is existing, and of course when you come to your kind of planning, you have to go into more details. For instance, all these wind farms they are planning and also building. There it's very important to know the bedrock below when they fix their constructions, and then they need much more than this. This is just a demonstration that the data, the information is there. You have to go into the specific site when you really plan to put the construction or constructions there, and that it exists in our mainly national databases, but at the same time now the national agencies around Europe, or at least in the European Union, is now trying to coordinate its information, so we have the same kind of explanation. What should I say? That we use the same terms, because the maps looked at least a few years ago very odd when you compared between different sides of the EEZ boundary. They looked differently because we had different classification. Now there is a work to really organize this all over Europe, not only in the sea but also on land. Oh. One factor which is very often forgotten, in particular here if you live in the southern part of the Baltic, it's sea ice. Sea ice it can be very difficult for constructions. In my opinion, sea ice is not taken into account enough in the biological ecosystem modeling, for instance, because this changes a lot between the years, and also the start of the production period or biological period is some years very favorable because there haven't been any sea ice, and other years it starts very late because the sea ice has changed the start. And if you look at the light blue here, it's every year. this area is covered. It's the minimum ice extent during a winter, and a normal winter is this line, and then you can see you have it in several parts of the Baltic, and for at least for constructions, this is an essential variable to take into account. We have only observed once, and that was in the 1980s, 86, 87, that this area was ice covered, and during that period we had an ice cover all the way out in Skagerrak. And out here the water is very saline, so it means that it's fresh water coming on top of the saline water and freezing. But it was an extreme winter, and we had to assist fishing vessels because they couldn't go into harbor. The ice stopped them, so they were caught out here in the middle of the Baltic proper. We have time series going back to 1650s, but I'm only showing the observations for the last 50 years, and you can see that the year I mentioned, 86, 87, it's the largest ice extent we have observed, and before remote sensing and satellites, we couldn't observe the whole. So this is a unique value. Then we have had many winters which have been very weak and mild, and not very large ice extent in the Baltic. But it's variable, and it's really a factor which had to be taken into account when we plan constructions in the ocean and the use of the ocean. Waves. Everybody thinks that waves in the Baltic, it can't be, they can't be too large. The pictures are very small, but the idea with the picture, it's January to December, and this is calculations derived from wind data. So the wind data are analyzed and of good quality, and then the waves have been calculated. And if we look at January, you can see that there are areas which refers to rather high waves, and this significant waves. So it's an average of the largest waves for a period, and so there are even higher maximum waves. But here you can see that the orange is between 8 and 9 meters, and those waves you can't play with them. It's not very nice to be out there when you have them, and we have them during the winter month. During the summer month, it's being better, and then the high waves are coming back in November, December again, and you can see that the area in the southern Baltic and up to Finland is there we have the most severe waves, and they are with a height of 7, 8, 9 meters. These waves you also have to add to the sea level if you are interested in protecting land. I have said a few times that when it comes to the more detailed planning, the general information is not it's not enough. What we can get from our monitoring system, we have to make much more intensive investigations. And what if? Then we use modeling. So we observe, we model, and we measure afterwards to see that our calculation have been correct. This is one of the largest constructions we have in the waters in relation to the Baltic. It's the bridge between Sweden and Denmark. we have Malmö here and Copenhagen Airport you can see on this picture. What if, I have a small story here. It was, I think it was 1985, 86. I had invited the Ministry of Communication in Sweden to our research vessel to a day trip. And the minister also came. So, and when I was standing in a kind of corner on the ship, and suddenly he approached me and he said, "What will happen if we decide to build a bridge to Denmark?" So I really got the question, what if, directly from the Minister of Communication. He was a bit afraid. And if you have followed the discussions before they started to build it, and all the investigations and everything, you can understand that this was not obvious that it should be allowed. And in particular, our ecosystem colleagues were very worried about the Baltic. But using models, using observations, we could calculate and optimize the construction and minimize the effect on environment, because there was a political decision about a zero-level impact. So for instance, this artificial island, it looks strange, but this is the boundary of a protected area. So they are building made the island exactly outside the protected area. This island they had to build because there it goes down into a tunnel and coming up on the Danish side. And the calculations, were they correct? Because we couldn't measure the effect before, but afterwards there was a long monitoring program, and I think that this is one of the most extensive programs, planning activities and then monitoring we have experienced. We have a similar between the Danish Isles, and there is now a connection between Denmark and Germany under planning, and they are also there investigating in detail for the constructions and the planning. Another what if, which have got the title spatial planning, it is that it has been done several times. This is an example from Estonia, and you use models to calculate oil drift, and then take the statistics from a lot of runs, and then you can see if there is an accident, how much does it affect the coastlines with the oil spill. And then they have optimized an area. If the ships are moving in that area, the risk is minimized if there is an accident. We have done it for the whole Baltic, but that map is more confusing than this one. So different models in combination with existing data, which are always too scarce, is one of the tools which are used for planning. Baltic properties. It's called a sea, because it's salt to a certain extent. The most typical for the Baltic, and here it's very much simplified, it is a fjord-like system. We have a sill and a deeper part in. There is a lot of fresh water coming in, freshening out the seawater, and there is water coming in from the North Sea. This water is not flowing in continuously. And sometimes it's cascading into the Baltic. Depending on the density, in particular salinity, it comes in and forms layers in the Baltic. And if it's very heavy water, it gets stuck at the bottom. And if you ever have put water in a bucket, not clean water, but water in bucket, if it stands for some time, it starts to smell. It smells awful. It's hydrogen sulfide. And the same thing is happening here. When the water gets too old, the bacteria start to use sulfate instead of oxygen, and producing hydrogen sulfide, which is a deadly poison for animals and also for humans. This mixture of fresh water and salt water creates a gradient from 35 PSU or salinity units to almost 1 up in the most northern part of the Baltic. This is a profile from north to the North Sea. And you can see the different layers with the different salinities. Here you have the what we call the Gotland Deep, one of the deep parts I showed in an earlier picture. So this formation of what we call dead bottom because of the hydrogen sulfide, it's a natural phenomenon. And even if we try, we can't get rid of it completely, but we can reduce it. Because the more nutrients, the more we stimulate the production and the eutrophication of the Baltic, the more material is coming down using the oxygen in the bottom waters. But we can't get rid of it. And oxygen deficiency, you can see the areas. I took a picture from 2011 because it's a rather typical situation. Where it's black, the bottom is dead. Where it's a bit lighter, it's too little oxygen for fish is avoiding those areas. And here we have a time series, and if you see the black part, it's the areas which have been covered which have been dead, covered by hydrogen sulfide. The red part of the diagram is the area which is below 2 milliliter per liter of oxygen, which is too low for most animals. This is the volume of the water which is influenced. So this is, of course, a severe problem. And when the salinity is too low, and also the oxygen values are too low, the cod eggs are dying. So it's really influencing the cod stock in the Baltic. We have discussed very much eutrophication, and it's depending on the increasing amount of nutrients. And I just wanted to show that it's very difficult to just give you one value of nutrients. This is an example for one spot, the Gotland Deep, which is here. You can see the island of Gotland and the Swedish coastline here. If you see the dotted line, or the black line is the average for a period from 1996 to 2010, and the dots are the monthly observations this year. And the small dots, which you can only see if you are close to the diagram, it's the area where we expect the variability of the observations. What is interesting for those who try to mitigate eutrophication is that phosphate, it's almost always phosphate in the surface of the Baltic. It's very low values, and if you in general compare these values, they are very low compared to Atlantic area, to the areas where you have a tide mixing up nutrients all the time. It's the dissolved inorganic nitrogen which goes to zero during the summer. This means that if we add nitrogen, we will increase the production. So the obvious idea, at least some years ago, was reduce nitrogen to the Baltic. Then we will decrease the eutrophication. But what happened when we started to decrease this even more, we got toxic blooms with blue-green algae, these very, very big blooms. And they take the nitrogen from the nitrogen gas from the atmosphere, and the dissolved nitrogen in the water. So it doesn't help if we take away the nitrogen, because there is always phosphate enough to stimulate these algae. And it's not just that we think it is. We had the opportunity to use a sewage treatment plant where we stopped the nitrogen release, and we opened the release, and we could see how this front of blooms were moving out and in. I haven't checked the time myself, but I'm at the end. I have worked with monitoring and creating observations in at least 40 years. And in my department in Sweden, I had the National Oceanographic Data Center. Wherever I were meeting planners or scientists, they complained about, we do not get any data. Why can't you give us data? Our data, they were free, so it was not a real problem. But where is the problem when you don't get the data? Yeah, the data is there in a database, in a computer, in a storage, but it's in an original format, and the user want to have a tailor-made extraction from the database. Somebody has to do that, and that money is not existing. We managed to convince the Swedish government to give us extra money, so now there are a few people doing this, serving data. We are working at Baltic level, at European level, global level, to really find systems to be able to release the data or to make data accessible in different ways. We are in this SeaDataNet project, which have been running now for 7 years. We are coordinating the National Oceanographic Data Centers in Europe, so they release their data in a format which can be collected, and you can go into SeaDataNet and really search the kind of data you need. Some of the data you will get automatically, some of the data you need a license, some of the data are closed of different reasons, but they are there, and the meta information is there. For many years, from 1902, we have had the International Council for the Exploration of the Seas. We have sent our data to Copenhagen, and ICS is a very good source for Baltic data, and also from other parts of Europe. And they also have products you can ask for time series, for instance. HELCOM has its database at ICS, but HELCOM has its own monitoring system in the Baltic, and is of course collected, and those data are monitored for the environmental management or protection of the Baltic. We are creating a new environmental climate database in Sweden, where I picked some of the information I have used in my presentation. And I really want to give you this example, EMODNet. It's a political decision, the European Marine Observation and Data Network. But I think it's the best development we have at the moment. I think it will be stable. It's building for the future, and it's built on a decision by the European Commission and the Parliament, which was adopted already 2010, and it's rather well financed. We are running a lot of projects of different kinds. I said about this sediment maps, coordinated sediment maps in Europe, improved. There is a lot of the chemistry about the physics, the data that are existing will be accessible through this system. It's expected to be ready 2020, but if you go into the website, you can see that there are already products. I choose one product, and it's using different kinds of databases. They have modeled the bottom habitat map. This is based on salinity and the sediments, and you can see the different kinds of habitats in relation to salinity, which is an important variable in the Baltic, both for the ecosystem and for other planning purposes. Thank you. I'm sorry.
Yes, thank you very much, Hans. I didn't want to stop you because it was really interesting, and I really wanted you also to talk about these things you know about. And please feel free to contact Hans, because you have to leave right away now after your lecture. And we would like to give you possibilities to now ask questions, but feel free to contact him after. So, is there anyone who wants? You have a question. That's why you're.
Yeah, a lot of questions. So from spatial planning perspective, so the first question, because you show this habitats modeling, that's great, because it means that all those data, oceanographical data, can be used also for other purposes, yes. For example, for biology. And my question is now, and I hope you know this balance project. So they made some proposals even to protect some sediments because they are so fruitful from biological point of view. But I want to ask you about sediments and maritime spatial planning, because according to the research we are doing here in Poland, sediments, they are fulfilling important roles. For example, they are filtering. So if you are making decisions on windmills, so what does it mean? That you are using these sediments, you are reducing them. And this is something which we are not aware as a spatial planner. So if you can say how to see this ecosystem services of your sediments, that's the first question. And the second question is, because you said about this salinity, that it's so important. Can you give us some hints? What does it mean for spatial planning? For example, whether if you build a lot of windmills, it can stop this inflow or not, or what we should avoid, in fact, in order not to change this inflow of waters and not to change these currents, because in such a case we can change all the building of the shore.
Yeah, if I start with the last question, one of the only arguments we could find to stop this gas pipeline from Russia to Germany, the only argument which was relevant was that it influenced the currents and the inflows changed the inflows of saline water. That was a rather weak argument, but it was difficult to find, let's say, rational arguments to avoid that pipeline. So of course all constructions are changing the inflow. The reason that it was so much discussion about the bridge and both between the Danish Isles and between Denmark and Sweden was because of we were afraid that we should change the inflow to the Baltic. From the beginning, we wanted to construct, to improve the Baltic conditions, because if we could avoid the real high salinities, then we should get a better salinity profile and a better mixing of water from the bottom and upwards, because the gradients got much less. This was up in the Danish Parliament, and then they said you are not allowed to do it better or worse. We want a zero solution. They didn't, and they used the word, we do not dare to play God. But there we had a real good planning situation where we could improve by changing the inflows. I will not go to any details here, but it's the most obvious case. If we, what is very odd in the planning perspective is that we spent millions of euros to make calculations for this zero solution from the bridge. But some years later, they built a windmill park just south of the bridge, with all these small platforms, and of course changed the flow of water. Not so in areas which are rather narrow, where you have a small cross section which is really defining the total flow, there you have to be careful. But in general, I don't think it's a problem. About the sediments, if there is a construction, and of course it will change the let's say the life on the bottom, and this was also very much discussed in connection to the bridge, and there was a fear that it should kill a lot of communities. The result was the obvious. Now it's real nursery areas, so it's really improving the ecosystem services in the region. So I can't really see what's dangerous from these constructions, if you don't make them too large, of course.
Yes, Larissa had a question about connected to the Öresund Bridge and the monitoring that was made in relation to that, and you were interested in the Russian part of the measurements.
Yes, when you show us the map of salinity, yes, I see that you are monitoring all bridges, not bridges of your country, but all bridges around the Baltic Sea, yes? And I want to know whose money is it for this project? Who pays for this job?
You mean the Baltic monitoring in general? Yeah.
Yes, around all Baltic Sea.
Yeah. There have been national monitoring since the regular monitoring since 1893. Mainly run by Finland or partly Germany from the beginning. From 1902, ICS established a monitoring network where the different countries around the Baltic took responsibility for their sectors. Then, of course, it was changing during time. But then, when we established the Helsinki Commission, we started what we call an environmental monitoring program, and then we used the traditional stations and continued them. And this was, we decided that in HELCOM committees that our contribution to the Baltic monitoring will be this, and then everybody was encouraged to go to the specific monitoring stations. This worked very well as long as we had the Soviet Union, because it was difficult to convince the Soviet Union, but when they signed the agreement, they kept it. And since the Soviet Union was strong, all the other countries kept it. But after the crash, so in the early 90s, several countries started to decrease their monitoring, and today I think it's a real minimum level compared to what we had 25 years ago. And it's really a pity, but it's continuing, and you could see from this map with nutrients, the black dots, that there are monthly monitoring expeditions in the yes, that one, in almost monthly. No, they are monthly. Yeah, and this we created it from. We started it from Sweden in the late 80s to have this monthly frequency, because the old frequency of ICES was 4 times a year, and it didn't fit at all for the variable climate in the Baltic. So we have run this kind of monthly monitoring since the late 80s, and now it's the recommendation from HELCOM. HELCOM is weak. It's not a directive as from the European Union. It's just a recommendation, and the countries has said yes in the ministerial conferences, but then it's up to the countries to do it. And Germany disappeared rather well to the west, the southwestern. Denmark disappeared completely from the Baltic, some after the crash of the Soviet Union, some countries couldn't afford their ships for the large monitor. So it's less today, and now it's not my personal concern, but I was very concerned a few years ago when I had the part responsibility for this. But it's paid by the nations as contributions. We have tried to convince the European Union to put more money into this, because they support fishery, the monitoring for fish stocks, but they are not supporting the monitoring for environmental purposes. Maybe it's good, because there are a lot of countries in other parts of Europe which do not monitor at all.
Thank you very much, Hans. Is there any further question, or you rather feel like a coffee break? It looks like. I think we instead, I was planning to have Andrei first and then the coffee break, but I think it's time to take a coffee break. So, and before that, I would like to ask Paula to come forward, because Hans is leaving us right after his lecture.
Yeah. And I'm leaving because I'm going to this CNET project, which has its annual meeting in Italy, and I'm one of the few international advisors to that project. So we are too few, so I couldn't stay here. It had been too obvious in the other group, and it was a misplanning from the beginning, unfortunately.
Yes, we are feeling really sorry for you that you had to leave such a nice company as we are here, and nice discussions. But thank you so much for coming and taking your time. Even if it was short, it was really excellent. So thank you. Here's also some.
Thank you very much.
Thank you. Some memory to keep us on the right course.
Oh, yeah, thank you very much.
So everybody grab coffee. We take a 20 minutes break. And during this time, do you need PowerPoint, or you are going to talk? You do it on the paper. Mm-hmm.
just want to show it now.
Yeah, you can just drag it anywhere. Drag it into the flash.
Hello? Okay, may I have your attention, please, while you are having coffee? Here is the schedule for the transfer to the airport. So please check whether you are on the list. Yes? And whether you like the hours of departure, especially for tomorrow morning. Not much, but so. So please check whether you are on the list, whether I have a right flights, yes, and whether this is my proposal. We can change it, but I think it's okay. You should start from the hotel something like 2 hours before your flight goes, except of the Wizz Air and Ryans and so on, because you should be earlier at the airport. That's why I put you, Sonia, so early, because you are flying with Wizz Air, yes, or something. So you should be earlier at the airport. Yes. So if there are any errors and when you want to change something, please inform me. Yes, because those are the transfer. I need to finish my tasks. So let's see whether I'm actually able to do this, because I'm not so much into PC. That's not the right thing.
What time do we have to be out of the room?
Today,
This hotel, yeah. By noon or 11 or noon or?
the room, it doesn't matter. It's more like we have a schedule and there is
You
one.
showed it on the.
You mean your room?
Yes, the room.
That's what the reception wants. I actually don't know, so you may not need
I'm
to
gonna get out. I'm gonna go get it out
grab
now.
your luggage. Yes. Usually it's 12 o'clock. But you can. I think what I would do is ask on the reception if you can get there, because usually they don't do the rooms until sometime in the afternoon. So,
Yeah, but that's okay. I'll just bring it down here.
yours is leaving at 10 to 2. Okay. Yeah. I think ask at the reception if so you don't have to rush. I don't know any Polish. I don't know whether they do the right. Wait. What happened now? Because I would like to have this one. I need to ask.
just drag it anywhere into the flash. It doesn't have to be under a file. I'll find it. Yep, anywhere. Okay, wonderful. That's all I need. Thank you. Thanks very much. T-shirts is on there already. Okay. Thank you very much. Great. Okay.
Może mam w tym, zaraz zobaczę tam w górze, tam stoi takie pudło i tam są mazaki, może jest żółty. Should I drag it or? Yes, this one. Ah, you are not the next one. Sorry? Darker. Pictures are not very good, and they should be. Also, I got quite a few of them. I mean, yes, but I know darker in the room. In the room. The problem is that you have to then start with. Yeah, well, he's not taking this. He's not taking your own. Okay, then we can switch. So much okay. Materials. Okay. I don't dare to be on the internet with this. That's a good reason. Oh yeah. You can switch slides with this. Yes. Okay. And we have some problems with
Okay. Damn it. I need it somewhere else. Where would you advise? Maybe I take it off and in my back pocket.
So we try to get everybody back into the room. I don't know where they have vanished. Guido is here, yes. Evgeny.
More or less.
We have a problem of time, yes, but of missing participants. I just take a short round out there, but maybe they're on the toilet or something.
So do I start or don't I? Okay. Well, the dynamics of the sea and coastal dynamics, that's a pretty tall order, and it would require quite a lot of lectures really to cover the whole topic, but I thought that just for this meeting, a few remarks that would help you to think about the sea as far as a planner may require that, which means some generalities which have some spatial sense. Well, first of all, a feeling. I'm jumping a bit between. Please excuse me. I don't have the ability of doing nice pictures in PowerPoint, so that's why you have it here on paper. The first thing which comes to my mind is one that we should remember, that the Baltic is a wind wave driven sea. There's a marked difference between the wind wave regime and swell wave regime, which is in the oceans. I mean, small seas, as a rule, are driven by wind waves. Large sea areas like the oceans, the processes, at least the coastal processes, but a lot of them, in fact, also are driven by swell tides too. Baltic is a non-tidal sea. The important thing about that is that, well, in fact, on the, say, ocean coasts, wind waves, true, well-developed wind waves occur, say, 5% of the time. The rest is swell. Waves generated somewhere far away from the coast or the place where they are looking, and they then become more oblique, nicer, and they have a quite different action on the coast. Wind waves cause erosion. Swell waves cause accumulation, in the very simple terms. So Atlantic or ocean coasts have a natural tendency to reconstruct themselves, while our Baltic coasts have the natural tendency to be constantly eroded because of the character of the sea. And now a little bit more about wave generation. If we have wind blowing from this direction, then it's not that waves are formed only in the same direction as the wind is blowing. Waves from that point generate in the whole half space, but their heights, or rather energy, which is in each of the directional components of the waves, is in accordance with this cosinus squared distribution. That is, on the here it's 1, yes, maximum energy. Here it's 0. Here it's very little, and so on, in very simple terms. But this is why, as a rule, the sea surface is never well organized. It's always a kind of random affair because of all these mixtures, of all these waves which constantly are there present. And it also explains why in some places which seem to be hidden behind a peninsula or something, you still have waves. Not only because they bend around the things, but because they are transported. For instance, Hel Peninsula, if you take the Hel Peninsula, here the Gulf of Gdańsk, and with this kind of wind direction, we get component waves coming also from to this point. They don't come from this direction, but they do come from these directions still, with this kind of wind. That's why we have quite large waves in this place. And the size of the waves depends, and their length depends, of course, on wind force, but it also depends on the distance along which the wind acts and the time for which the wind acts on the sea surface. Now, the Baltic is too small to achieve a fully developed wind wave during storms. We do have fully developed wind waves for, I would say, medium strength winds, something like 15 meters per second at most. But the large storms, during the large storms, if Baltic was larger, we could have had even greater waves than we do have here. So these 8 meters is simply, it's only 8 meters, which Hans has shown you, because the Baltic is so small. So this is, one has to remember that it's simply we don't have enough space, and we don't have enough time in most cases for in the occurrences when wind blows, for a fully developed wind wave regime, or fully developed wind waves on the sea. This is why we have these relatively smaller, though still very large waves. This is why the waves don't achieve their full length that they could have achieved in the ocean. The extreme wind wave on the Baltic is somewhere around, I think, 180 meters length. And this length of the extreme waves is quite important because the influence of wave action on the sea bottom or some layers in the water depends not on on wave height, but on wave length. And in theory, the theory which maybe many of you have, or some of you have heard, it says that wave action is felt up to down to half the wave's length going down. In practice, it's only a quarter of that wavelength. So if you have some calculations, for instance, in your area showing you that you have this kind of this size or length of wave acting in your area, the maximum, the average, and so on, then don't bother with these half wavelengths, just bother with the quarter. And even the quarter doesn't mean that anything very big is happening at this depth. Because this, please believe me, I calculated that. The currents resulting from wave action on this depth for the extreme waves, very large ones, are less than 1 centimeter per second. Now, 1 centimeter per second is not enough to move any kind of, for instance, sand, even mud. It can displace the mud particles only if they are already in motion, but they are not able to move it from a stable position. Yeah, now going to the coastline. Where's the drawing? I had one. No. Ah, yes. Oh, yes. The coastline. No. No. No, not the next one. Aha, yes. That's it. Well, the coastline. Yes, please do. The coastline. That's the ideal picture or cross-section of the coastline. Dune, beach, 1 sandbar, 2nd sandbar. And this is still a very bad picture, besides my being, I'm not an architect, sorry. But it's a bad picture also because it's still wrong with the dimensions. This part, that's the up to the 2nd sandbar, is about normal Baltic conditions. That's about 600 to 700 meters length from here to here. This part, beach and dune, is at most 60 meters in length. Now, I wanted to show you this. This, in most cases on the Baltic, is built of sand, just as this one is. Though, very often underneath there's a kind of, I would say, mother layer. Often it's clay. So there's a certain amount of sand on top, and then there's something which is not sandy, which is the existence of sand is important when we think about maintaining the equilibrium of a dune beach especially. So the important thing is that the most important things really happen here if we are to think about how we should, about the safety of the coast, maintaining beaches, dunes and whatnots. The whole thing, the whole game really goes here. It's maintaining these sandbars, in fact, that decide about the state of the beach and dune. The beach and dune, which are very well, we all love them for various ecological and nature protection reasons, but also because these are safety structures. They provide us flooding safety, for instance. Now, a little bit about what's happening along the coast and the sediment transport thing. The whole maintaining a balance or an equilibrium, an ideal equilibrium along the coast, especially if it's a more or less sandy coast, is about a game between the energy supplied to the coast by waves and I would say sand buffer, which is in front of the coast, which is there, the sand buffer, and in which also an important part plays the sediment transport. We usually are talking about sediment transport as something which is happening along the coast. It's not true. Sediments are not transported along the coast. Sediments are transported in a very haphazard way before the coast, but they do have the sediment movement has a resultant in a directional resultant. As a rule, on the Baltic, the resultant would look like that, with waves coming from here, which means that there's a component, as a rule, directed towards the sea. We are losing sediments to the sea constantly. And another one, a component, a longshore component. Everybody is talking all the time about the longshore, the longshore currents, longshore transport, and longshore transport streams and things like that. Rivers of sediments traveling along the coast from, for instance, some people were keeping saying that sediments are starting along the Polish coast. We put a particle near Świnoujście, that's the western coast, then it will end up on the tip of the Hel Peninsula. That's not true. Anyway, I'll come to that a bit later. Now, this game with sediment transport and energy, and it plays an important part also the composition of the sediments. So if the sediments, if even the composition, something changes in the composition of the sediments being in transport, then the coastline at once has to react to that. This results in some kind of change because the coastline has, as always, as anything in nature, it seeks equilibrium. That's the principal rule or canon really of nature, aiming at equilibrium. So with this kind of set of sediments, it's arrived at certain equilibrium, and if you disrupt this equilibrium, of course the system has to react. A typical reaction I showed you here is that on the way of the sediment transport there is some kind of obstacle. It can be a harbor, it can be a shallower bottom which forces movement of sediments out into the sea. It could be a change in geological structure here which causes a change in the composition of the sediments which are transferred along the coast. Well, if this obstacle causes some kind of stopping of at least a part of the transport, then the coastline has to react. It will bend away from energy. And this is the structural erosion that we may have in many places. This is why placing a harbor in a transitory in terms of sediment transport coast, you get the effect of very strong erosion. But this erosion is much more than just local. Up to a certain time, it was said that these ports cause only local erosion. It's not true. They cause a complete change of the system. And a lot has to be done, and it's quite costly to restore the system to some kind of fairly safe new equilibrium. Now going back. These are, of course, only a few tips I'm giving you, but maybe this is about the haphazard way the sediments do really travel somewhere in the coastal zone. We call that in Poland. We came up with the similar ideas in the early 80s, but later on it was also developed within a European, the Eurozone project, where they call this thing circulation cells, quite rightly. So it's because along the coast we have certain obstacles. Once again, these may be ports, these may be erosional platforms, shallower areas which extend seawards or something like that. And they form obstacles to not sediment movement is the result of water movement, in fact. So they are obstacles to water movement in the system. And this water movement then goes like that, and it moves the sediments. It moves the sediment. Of course, it cannot, water cannot very often go across the boundaries. It has to go along the boundaries and forces the sediments out. Now, the sediments which are forced out to the sea, only a part of them can come back because they have to fight gravity. Simply, back are coming only the finer grain sizes. But the finer grain sizes are not stable in this very active part of the coastal system. So, in effect, they come in, but they are lost. There's also, that would be too much. If anybody wants to know a little bit more about forcing by water in the breaker bar system, then we can discuss it separately. But that would be too much. Now then, there's this other effect one has to remember. Erosion accretion system. If you get an accretion somewhere, so accumulation, then behind that accumulation it causes an extension of the isobath, or a kind of extension, shallowing seawards. With that shallowing, this is a disruption of the transport system. So behind that there has to be an erosion. This erosion provides additional sediments, more than maybe the energy of the waves, not currents, waves or wave-induced currents can transport. So we get accumulation. But because of that, we get erosion and so on. So once you start something, it can take a long part of the coast to become really attenuated and become really invisible. One has to remember about that. Don't bother too much. And don't be afraid too much if you see these things. But they are natural and have to happen. And I suppose, I would like only to make a remark on some, because I hate the myth beliefs. There's a typical belief also that cliff coasts are the suppliers of sediments, important sediments for the near shore zone. No, this is absolutely not true. Cliffs are, as a rule, built of material of in the structure of cliffs, typical at least on our southern coast, also Lithuania and Latvia, there are any. The sand content, which is useful for the coastal zone and protects the beach, does not exceed 10% of the cliff body. The rest is clay and till. So which, if eroded, is taken away by waves to the extreme depths and produces that mud we have in Gotland Deep and Gdańsk Deep and all these deeps. Only the sand stays at the coast. Now, with the 10% content of sand in a cliff, I will give you the values. 1 kilometer of a 25-meter high cliff, if it is eroded 1 meter, if it retreats 1 meter back, produces 2,500 cubic meters of sand. Now in the front of the, for instance, cliff in Jastrzębia Góra in Poland, we have a sediment transport of about, I would say, about far over 250,000 cubic meters. And this gives you the relation and the true importance of cliffs as a supplier of sand to protect the coast. Okay, that's a smattering of the things.
Now, are there any questions from the audience? Jacek already has one. You're always first.
I have a question because I don't understand anything, I must say.
Oh, I tried to.
That's a problem. My problem. Can you tell in very simple words, Andrzej?
Yeah.
We have different type of coasts. What does it mean for spatial planner? Can we build any structure behind the Swedish coast because it's rock? Should we look differently on Polish, Lithuanian, Latvian, Estonian coast because it's sand? What type of thinking is important for maritime spatial planners? For example, windmills, can they distract these natural processes of coastal dynamics? For example, damping. It is important where you put damping and what is the problem with damping, or we should not care as the spatial planners about damping. Should we take care of dredging, or it's not important? Can you be more specific, because I'm lost?
Well, I tried to tell you about I also should have said that there are processes which happen in the sea or on the coast, which are in different scales, in temporal and spatial scales. But okay. can we build? Of course, we have to take into account that we are in the south behind the dune coast, and in the north, in most cases, we have also dune coast, but a lot of uplift, geological uplift, and so the reaction of the coast could be different. But simply what I'm saying, that the things, for instance, the dune system, or in fact any other system, requires a certain amount of space, and which has to be protected simply for safety reasons. And you should not encroach on this space by development. If development encroaches on the space for safety, and this goes as well in any country, also in Sweden, I'm sure, or Finland, or anywhere, then you are in trouble. Simply, the investors are in trouble because they can't be protected against the safety. And the safety, the amount of space needed for safety depends on the kind of protection or the type of protection we want to introduce. Is it nearly natural, or is it strongly technical? Then with these technical measures, this means that some of the natural values could be impaired, let's say, kindly. The dumping thing. The dumping thing, to a large extent, is dependent, of course, on the quality of the bottom somewhere, but also on the influence of wave action on the bottom. Dumping can be done because, first of all, it's not allowed very much now. But storing sand for future uses, for instance. And selection of the site has to be done in such a way that the wave currents don't cause that the sand is transported out of the storing site. Yes. So this kind of approach, always one has to remember how far waves influence the bottom. And as already Hans has said, in fact, the other currents in the Baltic acting on the sea bottom or anywhere else are rather weak. So, in fact, we mainly have to deal with wind wave currents, which act on a limited kind of depth. Really, this depth, I said 1/4 of the wavelength, but for practical reasons, I think when we say that not more than 25 meters, that's just as well.
So we're talking about the coastal zone mainly, and some
well,
areas that are deeper.
if we talk about the influence of wave action, we talk about the Baltic anywhere you want to think about it. Of course, what I showed was mainly concerning the coastal zone, because I was supposed to say something about coastal dynamics and
But anywhere where it
spatial
is
effects.
less than 20 meters in the Baltic, that's where we have to be aware of it.
When it's less than 20 meters, we certainly have to be very aware of the wave action effect.
One more question?
Yes, I have a question. Southern part of the Baltic Sea has this sandy coast, and
Yeah.
you also said it's waves cause erosion in this sandy part. But okay, and we also have this underwater part, and underwater part there are these stones and Baltic Sea reefs. How do you think this part, what is underwater, is it big importance, or maybe not so big importance how narrow or maybe how wide it is. So maybe this underwater stone somehow to mitigate this wave effect to coast. And if we remove those stones from bottom, then it might cause more erosion than before.
Well, of course, the Baltic has its Swops Bank, for instance, or any other banks. And of course, removal of these banks would result in a different generation of waves. That's though, and the reduction wouldn't be. Well, I did some calculations once, and it appeared to me that, for instance, for the coast, the central coast of Poland, the existence of the Swops Bank has the result of some 10% reduction in wave height in a certain area. Yes, because of course, these shows cause loss of energy of the waves which are propagating over them, and then they have not enough time to reconstruct themselves after that. Yes, in the wind field.
Yes, I think you. Is there anyone else with another question? One more? Okay. Then next, I would say we have a very short break. Open the windows, just the leg stretcher. And then it's time for Sonia to have the floor for.
Thank you very much. It was very interesting for me. What do you think about St. Petersburg dam?
I think it's not a coastal dynamics problem, it's an ecological problem rather, and pure hydrotechnics. So I can't say anything really. I know very little about it. I only think that it's a case of water exchange, things like that. Isn't it? As far as, on the other hand, if you ask me because you want to have my opinion whether it's right to do something to protect St. Petersburg against flooding, and it's very difficult to imagine any other kind of solution that would save St. Petersburg from flooding. And in fact, you have, up to a point, copied what the Dutch have done for their coastline. It's only a case of allowing for proper flushing and exchange of water in between the times when the dam is closed.
Okay, thank you.
Thank you.